Hello and welcome. This is going to be our lecture video for October 9th. Let's go ahead and get started. Our goal today is to be able to use matrices in the calculator to solve word problems involving systems of equations. Why? It's often going to be the fastest method and it's going to help you avoid mistakes. Let's practice with just an algebraic system of equation here with three variables. You can pause the video and copy this one down if you want. Now, this is not ready to be put into the calculator in the form of a matrix yet, and that's because the equations are not in standard form yet. But we can do this in one step if you just remember the simple rule that if a term moves past the equal sign, it needs to flip its sign. So I need to bring all the terms with variables to the left side of the equal sign and put them in alphabetical order. So that top equation is going to become 5x plus y minus 2z equals 11. Notice the 5x was negative, but now it's positive. The 2z was positive, but now it's negative because I had to bring them to the other side of the equal sign. The second equation is already in standard form, so I can just leave it alone. And the bottom equation, we've got to do a few moves here. We've got to bring the 2y over and the 3z over, and they flip sign. And now we have a system that's ready to be turned into a matrix and put into the calculator. When we turn it into a matrix, we just keep the coefficients and we drop all the variables, addition signs, and the equal sign. So that top row becomes 5, 1, negative 2, 11. The next one is negative 2, y, I wrote y. The coefficient on y is 1, negative 2, negative 3. And the bottom one is 1, 2, negative 3, 1. So here's our matrix. If you have systems that are skipping a lot of variables, it can be useful to label what each column is so that you know where to put those zeros. And then the last one is always the constants on the other side. All right, I want to plug this into my calculator and then run reduced row echelon form on it. So let me go ahead and bring up the calculator. I go second, matrix, and then over to edit. Now I've already plugged in this matrix into the calculator, but if you hadn't, you would make sure you had a 3x4. You plug in all of the numbers, hitting enter in between. Then you would leave this part of the calculator by hitting second quit, and then immediately go back into the matrix by doing second matrix. Go over to math. We want to pick reduced row echelon form, which is option B, and then into the matrix a third time to select the matrix that we just edited. Press enter, it runs that operation on the matrix and spits this out. The fact that we got the identity matrix on the left means that the function ran correctly, that this does have a solution. And then down the right-hand side is the ordered triplet, or it's the value for x, y, and z. And the fact that they're all integers is a really good sign that we did this right. So 2, negative 5, negative 3. Let's just write that down. 2, negative 5, negative 3. We can put some parentheses around it, make it an ordered triplet. And that is the point where the solution planes for these three all intersect. All right, here's a fun one for you if you want to try a 6-variable system. Quick question, are there enough equations here to solve for all 6 variables? Well, the rule is we need as many equations as we have variables. So we have 1, 2, 3, 4, 5, 6 variables. So we need 6 equations, 1, 2, 3, 4, 5, 6. So this should be solvable. Another kind of question to think about is what if we had 7 or 8 or 9 equations? Are more equations better? Well, it kind of messes with the calculator if you try to plug in too many equations. So you would just pick 6 of them to put into the matrix and leave some out. Now, if you got something like an infinite solutions or a no solutions, then maybe try a different combination to make sure that the system doesn't have just one solution if you pick a different combination. But most of the time, you're just given the correct number of equations to solve it. It's just useful to double check, especially with these bigger ones. Okay, so what size of matrix are we going to need in the calculator for this? So I'm going to go second matrix over to edit. What I'm going to need is a 6 by 7. 6 rows for the 6th equation, 7 columns for the 6 variables plus the constants at the end. Once you got these all plugged in, you go second quit, back into the matrix, pick the correct function, into the matrix one last time. This time I saved it as matrix B. And if you did it right, you should have a matrix that matches mine. For this system, A equals 1, B equals -2, C equals 3, D equals 4, E equals 2, and F equals -1. Now this is somewhat time consuming to plug in all of those numbers. I mean, you're plugging in 42 different numbers. But just for a second, think how difficult this problem would be if we tried to solve it using elimination, for example. What you would have to do is pick 5 different combinations of 2 equations and eliminate the same variable in all of those combinations. That would take a long time, and all that would do is just simply reduce the 6 variable 6 equation system down to a 5 variable 5 equation system. Then you'd have to repeat it, going all the way down to the point where you can solve for 1 variable, and then plugging them all in all the way back up to the point where you're plugging in 5 different variables to solve for the last remaining variable. This problem would literally take hours to complete if you tried to do it by hand, and we can do it with matrices in the calculator in a matter of minutes. So matrices really are better, especially when we start to get to these very large systems with a bunch of variables. Okay, now I promised some word problems. We're on to some word problems. In a collection of coins made up of dimes and nickels, there are 3 more nickels than dimes. If the collection is worth $1.95, then how many of each type of coin is there? All right, so first thing I need are some variables. And don't just say D equals dime, N equals nickels. Be more specific, say D equals number of dimes, so that you don't get confused thinking D is like the value of a dime or something like that. And N is number of nickels. Now that first sentence is kind of tricky to represent. There's 3 more nickels than dimes. So think, how would I have to balance this? Start with just nickels equals dimes, but there's 3 more nickels than dimes, so in order to balance it, I have to do the +3 on this side. Because there's 3 more n's than d's, d plus 3 equals n. For this to be balanced, the +3 has to go over here. A lot of the time, just reading that, we accidentally put the +3 on this side, but that's not accurate to what the problem is saying. And then just double check it. If I make n equal to 10 and d equal to 7, well then there's 3 more nickels than dimes, and this would balance. All right, the collection is worth $1.95. So now I have to take the variables and multiply them by their values. So 0.1 for a dime plus 0.05 for a nickel. Add them together, I get 1.95. This isn't quite ready to become a matrix. I need to subtract a D over to this side. Equals 3. Now I can turn it into a matrix. 0.1, 0.05, 1.95, -1, 1, 3. I'm going to go ahead and pause the video so I can plug this new matrix into my calculator. Alright, so as you can see, because it was a 2 variable, 2 equation system, I had to use a 2 by 3 matrix. I've plugged in all the values there. Let's run the operation on this. Saved this one, this matrix C, because I wanted to just save A and B to be those size matrices, and if I'm doing a 3 variable problem, I'll overwrite A. And I get 12 and 15. Now I've got to figure out what that actually means. So 12 and 15, which one's dimes, which one's nickels? Well, this row was for dimes, this row was for nickels, so it's got to be 12 dimes and 15 nickels. And that makes sense with that first sentence. There are 3 more nickels than dimes. So there's 15 nickels, 12 dimes. Yep, that works out. 12 dimes would be $1.20. 15 nickels would be 75 cents. And together that makes $1.95. All right. Here we've got a triangle. The second angle of the triangle is 50 degrees less than 4 times the first angle. The third angle is 40 degrees less than the first. Find the measure of each angle. So we'll say x equals the first angle, y equals the second angle, z equals the third angle. All right, so the second angle, so that's y, is, so that's an equals sign, 50 degrees less than 4 times the first. So 4x minus 50. The third angle, so that's z, equals 40 degrees less than the first, so x minus 40. But I've got 3 missing variables and only 2 equations. What's the last equation? Well, this is our triangle sum postulate, that the 3 interior angles of a triangle have to always add up to 180. So we have to use this fact from geometry to get one of our equations. Kind of tricky. All right, I'm going to move the 4x over in this equation. I'm going to move the x over in this equation. And now turn this into a matrix. 1, 1, 1, 180. Negative 4, 1. We skipped, there's no z, so we got to fill in a 0. Negative 50. Negative 1, there's no y in this one, so we fill in a 0. 1, negative 40. And I'll pause the video again to plug this one in. All right, so I used matrix A, which is already a 3 by 4, and just overwrote the numbers in there. Now let's go through our procedure to simplify that matrix. And we get an angle of 45, 130, and 5. So now I just have to figure out which is which. So the first angle was 45, the next one was 130, and the last one was 5. If we look at this really skinny one was probably the 5-degree angle. The one that's past 90 degrees, the obtuse angle, has got to be the 130, and then this acute angle in here has to be the 45. And that actually kind of lines up with what we're seeing in this picture, so that's another good sign that we did it right. That degree marker looks like a 0, so I'll just erase it. Okay, that's that for this video. I'll embed another one for you to try. Have a good rest of your day.